which is what? What are the atoms in a water molecule? Hydrogen and oxygen, okay? So you guys have these things going on, right? Okay, chemistry. So if you work strong in chemistry, this is how we sketch out models. We use the element symbols, okay? I did not actually have to draw the circle. Okay, we'll just leave it like that. Okay, these indicate a bond, always a bond. If you see a line, it's a bond. I'm saying that because you'll have more chemistry coming your way. So a line equals a bond. In this case, the bond is covalent. There's other bonds called ionic. Two types of bonds that we will be talking about for biochemistry, covalent and ionic. This is a covalent bond. Now, I don't need you to differentiate that or know that specifically right now, but I do need you to know that that line means that that's what it is, because a bond takes a lot of energy to break. So can I just grab your hand like this? This is a bond. I'm actually glued, okay? It's going to take a lot of energy to break me away from her. And I say that because the pool itself, when we're looking at water, it's not just bonds that's being formed here, that's part of this equation, but when you have multiple water molecules, they started forming attractions. So what were these attractions called? And it's kind of confusing based on the name. What were these attractions? When other water molecules come together, okay, remember how they were laid out? And you guys pull out your Pogels if you want. Okay, I'm just going through what you guys went through the other day. Okay, so if you need to refer back to your notes, go for it. Take them out of that notebook you have. Okay, when another water molecule is here, how is it going to arrange itself? This is one of the chemical properties of water that make it so cool and so special. Laura. Perfect, okay? And what word did you use there when you talked about the oxygen and hydrogen? What word? Attaches, okay? So it attaches. I think I can go with that. Okay? So we are attaching to that hydrogen and oxygen, that hydrogen of another water molecule. We're attaching. I'm going to call it attached because that's what a Laura used. Is attaching as strong? I'm going to attach to now, okay? I can attach like this, okay? I'm attached to you. I'm just standing next to you, okay? But I'm attached, right? Because we have like contact going on. Is it, for those that can't see on this side, sorry, we're attached. We're still having contact. Is this easier to break apart or harder than okay, it's easier to break apart because it's not a true bond. However, this attachment has a special name that makes it confusing because what is this attachment technically called? What?
A weak attraction.
It's called a weak attraction. I believe it said it in your Pogel. It's a type of, they called it something bond. What kind of bond did they call it?
Hydrogen.
Yeah, they call it a bond, right? They call it a hydrogen bond. But we're saying it's not a bond. It's just a really good attraction, okay? That gets confusing, and I'm spending some time on it because when we look at molecules later on, like DNA, okay, it is these hydrogen bonds that come into play, and it's the ability to not be as strong as one of these that help make it easy to pull apart, okay? But in the meantime, we need to know that these attractions are forming all the time in water molecules. Because water, why do these attractions form? Because what is special about water that not all molecules have? It's a neutral molecule. It's not an ion, so it has an overall charge of 0. If it's neutral, what do we know about the protons and electrons? What do we know about the positive and negative charge? If the overall charge on this water molecule is neutral, what do we know must be true about the positive and negative charges within this molecule? they cancel out, okay? So, positive charges equal the negative charges, so they can cancel out. Do you guys agree with that based on what you learned? Okay. Now, if you are confused here what I'm talking about with positive and negative, it goes back to protons and electrons. If that part is tripping you up a little bit, I have an optional video I'll put up, just like a chem basics, like the structure of an atom and when they form bonds, what's going on there, okay, to review. But what I need you guys to know is that there's particles called electrons. There's electrons and protons for oxygen, electrons and protons for hydrogen, electrons and protons for this hydrogen. But when they all come together, there's the same amount of electrons as protons. They cancel out. But is there an even distribution of these protons and negative electrons? Even though the whole thing, if we were to look at this whole thing, it's 0. Are they evenly surrounding? Look at your figure 1 in your notes. Are they evenly surrounding that molecule? Is the negative charge evenly spread around this entire molecule? This is figure 1. Look at your notes, those that are looking at me and waiting for me to answer. And I am more than 6 feet away from you guys. I am going to take my mask off. Monday I'll keep it on, but what do you guys, look at figure 1. If you don't remember, figure 1, the very first one. What do you guys notice in that picture, and you noticed it on Tuesday? Is the negative charge evenly spread out around this water molecule? No, it's not. Where is most of the negative charge here? Perfect, thank you. Okay, so it is more negative. I'm putting this symbol, you don't need to know what that symbol means. You can look at what you have there, but that means it's more negative. That means the negatives like to hang out over here. And this is a chemistry principle that we're not going to spend a whole lot of time in, but it will be in that video I give you if you want more clarity. But it's because of where it's at on the periodic table, if you remember trends. It's because of its valence electrons. It's because of the size of it that there is more of the negative electrons concentrated on this end than the other end, okay? What do we call these molecules like water that have this uneven distribution? What kind of molecules are they? Well, you're looking it up because that was a definition on there. Yes, it is. It's polar. And here's the deal. I'm not a big hand raiser. Okay? You don't need a hand raise. You can throw out answers. And it's kind of nice because that way, especially when we start wearing masks, people might not know. Like, I'm not calling on you. You can throw out an answer. It could be wrong. And it's not as high stakes. You know what I'm saying? Because your name's not attached to it. So feel free to throw out answers, wrong or right. Got it? Okay. So this is called a polar molecule. So all the stuff that I'm writing right here, if you want to add it, if you want to highlight it on your POGO, the points that I'm talking about, I encourage it. If you're kind of quiet because this all makes sense and you just know it all, yay, okay? But if not, this is that part that separates those that are going to push it above and beyond and those that are going to stay mediocre. Does that make sense? You need to add these details in. It's not just about the concepts. So this is called a polar molecule. A polar molecule has, I'm going to call it uneven distribution just because that's what the POGO called it. I want to keep it the same. And it's due to the position of the electrons in that orbital. Okay? But we can't confuse it with a true ion, which is completely different because it has its overall charges positive or negative because it doesn't have the same amount of particles. I'm going to only spend a couple more minutes. I didn't have a timer set for this quick teach, but I know we've been here for a bit. Polar molecules. We can remember that polar molecules include water. That water is, let me rephrase that water is a polar molecule. It is the prime example of a polar molecule. It is small. It is everywhere. It is necessary for life, okay? It's necessary for non-living things to be used. It is basic essential when we look at other planets for possibilities of life. That is the first little molecule, this little dude here that we need to think about. And we can remember that it's polar because what do we call the cold form of water? Ice. And where's there a lot of ice located on the earth? Antarctica. And what do they call those ice things, those, I won't say not glaciers, but those ice things, those ice tops that are ice caps? What kind of ice caps? What? Polar ice caps. Okay, so think polar, think ice, think polar bears up there, you know? Ice is a form of water. So can you always remember polar molecules? Water is a polar molecule. So when asking yourself if something is polar, think, is it like water? Does it have an uneven distribution? More negative on one side. Cool with that? Okay, it's because of that it's able to form hydrogen bonds, these weak attractions. And I'm stopping there because that was a long time to teach.